Okay, so now let me start. First, some announcements. Those who have not yet collected TA, they can collect it from the office after my talk. Second thing is, after my talk, please hand over the feedback form at the time of collecting the participation certificate. Participation certificate will be distributed outside at the end of after my talk, along with high tea. So you can, at the time of collecting, please remember to give the feedback form. We want to hear from you, we want to know your opinion and suggestions for improvements. Okay. All right, so now let me start my talk. This is just called Galois theory. So, what I am going to do is first write the main theorem of Galois theory, and then I will explain the various notions that enter into the statement of the theorem, and then illustrate it and explain the theorem a little more. Okay. So, that is the plan of the talk today. Usually I start the topic with example, but this time I decided that first I will make the statement and then I will give examples. The entire lecture, remaining part of my lecture will be explaining through examples various concepts that enter into the statement of the theorem. Theorem. So, let capital K be a separable normal extension, let us say finite extension of a field small k. Let G be the Galois group of k over small k. Okay. Then there is a correspondence, there is a bijective correspondence so between what? So subfields, so the set of all subfield F, so that means contained in K, K contained in F, contained in K. On the one side, on the other side, yeah, subgroups H contained in G. And it is not enough if you just say there is a bijection from this set to that set, but what exactly is the bijection and how is that bijection established, and if you take some special kind of subgroup, what kind of thing that you get here on this side. So, that is what we are going to explain. Okay. If you take a field F, that corresponds to the Galois group of, I will explain all these terms. I am just first I am writing down the statement. Okay. In case you have forgotten what is Galois group, do not worry, it will be explained in a few minutes. Galois group of K over F, and that will be automatically a subgroup of Galois group of capital K over small k. And yeah, on the other hand, so this is our G. Okay. On the other hand, if I take a subgroup H contained in G, then this gives you a certain field. What is that field? It is a fixed field. F is equal to k power h. Okay, so I need to explain this, all right, and yeah, there is, suppose I take a normal subgroup n, then I get a certain field F. F is a Galois extension or same as separable normal extension. Let me write this as Galois extension. Galois extension of small k with Galois group gal f over k being equal to G mod n. You can say, yeah, so this is a basic theorem. You can make a slightly more precise, you can write out immediately what will be the degree of the extension of f over small k, and that will be the same thing as the index of the group H, in G. Okay. So, I do not have enough space to write it, and anyway at the moment I do not want to write it. So, what Galois theory does for you is connects up group theory and field theory. When you are given a field, you can look at all automorphisms of the field. Okay. So, you have a field, you look at all automorphisms of the field, all right. That says nothing about small k, but when we say Galois group of k over small k, what we want to do is we look at those small k vector space isomorphisms of capital K which are field automorphisms. In other words, capital K is viewed as a vector space over small k, and you look at k vector space isomorphisms which are also field isomorphisms. Okay. That is what is called Galois group of capital K over small k. The role played by small k is that elements of small k are not to be moved. Group elements, the automorphisms of capital K which fix every element of small k, you look at such automorphisms, that is called Galois group of k over small k. Now naturally, so this is going to you can think of G as I said, vector space automorphisms of small k over capital K. When I write like this, it is just vector space automorphism, okay, but I am looking at field automorphisms, okay, and then the possibilities are highly restricted. So much so that it becomes a finite group, because we assume that K is a finite extension. K as a vector space over small k is finite dimensional. When that happens, all right, the group, this Galois group of k over k becomes a finite group. Now you have a bigger field capital K over small k, and you want to understand what are all the possible fields that K can have, subfields which contain small k, all right. I am going to do work out lot of examples, then you will see all these things. And what this theorem is saying is that, look, there are as many subfields as there are subgroups, and there is a correspondence. I give you a subgroup, you can construct a subfield. You give me a subfield, I can construct a subgroup, and it behaves nicely. So there are special type of groups, normal groups. So normal subgroup makes sense. What is a special property of the field? That itself becomes a finite separable normal extension. Okay. So this is a special type of subfield. Okay. So this is the what is called Galois correspondence. Now you take a smaller group, if H here is smaller, okay, the field will be bigger, the corresponding field will be bigger. So, it is inclusion reversing. If H contains, say, let us say some K, then, so the K is not the right word to use, so H prime, then I will have, so when you take a smaller group, the field, corresponding field F prime will contain F. So, it is inclusion reversing. On this side you take a bigger group, that will correspond to a smaller group. So, that is a type of inclusion reversing correspondence that we have. Now, I am going to erase only this portion, but explain the words that I have used here. After giving these basic definitions, I will do examples. So, separable. Okay, so let us take this. What do you mean by separable? So K is a field. So we draw a diagram like this: small k, right, like this, capital K, bigger field that contains small k. We say this is separable over a small k, means the following. I take an element alpha in here. Take any element alpha in capital K. See, this one is what? Finite extension. What is the meaning of finite extension? That should what I should have explained first. That simply means that dimension of capital K as a small k vector space is finite. See, capital K I can think of as a small k vector space. So therefore I can ask what is its dimension? It is finite. So that's all it's saying. So if I look at this 1 alpha square dot alpha power n is equal to dimension of capital K over small k, which is finite. Now I have written down n plus 1 elements and k is n dimensional, therefore that must be linearly dependent set. Therefore there should be a linear relationship among that, and that same thing as saying alpha satisfies a certain polynomial. And look at the smallest degree polynomial that alpha satisfies. Among all possible polynomials that alpha satisfies, there will be one that is of smallest possible degree, and even that may not completely fix the polynomial because you can multiply by a scalar. So I say monic polynomial satisfied by that. That will be an irreducible polynomial over small k. You cannot further factorize it in small k. Okay. So now I have given an element, I have associated a certain irreducible polynomial. Okay. Now if that polynomial has no repeated roots, then you say it is separable. This is a purely characteristic positive phenomenon, or failure of that can happen only in the case small k, only in the case of positive characteristic. In characteristic 0, every extension is separable, no need to worry, automatically. Okay. You understand? Because if you write down in I should now I think give an example of something which is not a separable extension. Let me give an example of that. So we want an example of a extension which is not separable, and there you will understand why it is so. So let us look at the field small k to be, well, we all know Z mod Pz, right? Okay. I do not want, first of all, forget this. This is a field when P is a prime. Yeah. So I take k to be round bracket T. What is this? This is field of fractions of, so that is field of rational functions in just one variable. Is that clear? So how will elements of this look like? It will look like, this is going to look like some P of t divided by Q of t, and Pt, Qt, they are all polynomials, as you saw in polynomials in T, coefficients from Z mod Pz, okay, and Qt not equal to 0. That is how it will look like. Okay, this is, take this as an example of a field. Now consider the polynomial x power p minus t. You cannot factorize it in here. There is no way you can factorize it. Okay. Now take it, so let us call this f of x. This is a polynomial in where? This is in k, this in k, well, k square bracket x. It is a polynomial in x with coefficients from k. Alright. Now look at f dash of x. F dash of x is what? You just compute the derivative the usual way, except anytime you see some multiple of p, that is to be set equal to 0. So this is px power p minus 1, that is it. But p times anything is 0 because you are in characteristic p. Okay. So now you see fx and f dash of x, see f dash of x becomes identically 0. Okay. So in particular, if x naught is a solution for this, then if alpha satisfies this equation, then same alpha also satisfies this equation, which means that alpha is a multiple root of this. So that is the failure of separability. Separability means an irreducible polynomial should have no multiple roots. But here you see that alpha, if it is a root, then it is a multiple root. In some extension field always you will have some root. Okay. So all said, if you are, so this is the only way it can happen in some precise sense, that I will not make it any more precise. So let me make this remark. In characteristic 0, any extension of k is separable. So no need to worry if you are working with rational numbers or real numbers or whatever, separable. So this condition you can more or less forget if you are working with characteristic 0, just forget about it. Alright, next is normal. So what is the meaning of normal extension? Okay. Sorry, I erased this in characteristic 0. Characteristic 0, any extension of k is separable. So, but before I describe what is a normal extension, maybe I should do an example, then things will become clear. So let us take small k to be rational numbers and capital K. I am going to do two examples. Let us keep all these examples somewhat elementary. Let us say root 2 or maybe root 3. Everybody knows this is a field, right? It's just, I am just adjoining root 3. Root 3 is an algebraic number, therefore it is a field. Okay? And in fact, this field is isomorphic to, you take q square bracket x divide by the ideal generated by this x square minus 3. Correct? So this x square minus 3 cannot be factored in here. So it is an irreducible polynomial. Moment I have an irreducible polynomial, the ideal generated by that is a maximal ideal. Ring I have PID modulo a maximal ideal, that is a field. Any ring modulo a maximal ideal is a field. So it is a field. Alright. Now what are the roots of this? What are the roots of this x square minus 3? Only plus root 3 and minus root 3. And we attach plus root 3, automatically minus root 3 is also here. Correct? So we say that this is a normal extension. Okay. This is a split. Okay, this expression also is something we will need. Splitting field of x square minus 3. Okay, this meaning capital K is a splitting field of this. What is the meaning of splitting field of a polynomial? If you can factorize that polynomial and completely into linear factors, okay, in that field, but not in any smaller field, then you say that this is a splitting field. So let us look at something which is not a I still haven't defined what is a normal field, normal extension. I am going to do that. So let us look at this example. K is still Q, but capital K is this time Q attach say cubed root of 2. Okay. Now this you also recognize is isomorphic to the field which is Q square bracket x modulo x cube minus 2, and this again cannot be factored in Q. This has no roots in Q. However, we know how to write the factorization working with complex numbers. So over complex numbers you can write x cube minus 2 as x minus 2 power 1 by 3 times, okay, x minus, let me write here omega 2 power 1 by 3 x minus omega square 2 power 1 by 3. What is omega? Omega is the cubed root of unity. Omega is primitive. Okay. Now, so all right, what is the point of this factorization? You see, now you have two other roots. These roots are not here. Why is it not here? If omega 2 power 1 by 3 is here, okay, suppose omega 2 power 1 by 3 is also here, then what happens? 2 power 1 by 3 is there, and therefore omega should also be there. But this is a subfield of real numbers. See, this is entirely K is, so K is contained in R. Omega is a complex number which is not real. Omega does not belong to K. So this implies this other fact omega 2 power 1 by 3 cannot be in here in K, and same with the other one. Now you see, let us look at the, I erase this. Now you see I have another field, namely the following. Let me erase this. Consider this field K1, let me call it E maybe. E, this is Q attach omega 2 power 1 by 3. Of course, this is contained in complex numbers. Now, okay, this also I claim is isomorphic to the same field Qx modulo x cube minus 2. You put x is equal to omega 2 power 1 by 3, this polynomial is satisfied because I have factored it in here. Do you see that? Is that clear? Omega 2 power 1 by 3 is also root of the same polynomial. So I have another field. Now this time this E is contained in C. It is not a real field, it is not contained, it is not a subfield of R because I have written complex numbers. So what has happened is the same field embeds in the complex numbers. So the same, this field, okay, I have found two ways of embedding. E embeds in C, and of course K also embeds in C. K is isomorphic to E, but K is not equal to E. Now I will tell you what is a normal field. So you say an extension is normal if any time you have an embedding of capital K in the algebraic closure of K, all right. If you have two embeddings of capital K in the algebraic closure of small k, then the images are actually equal. The particular way you have embedded may be different, but actually they are equal, all right. So now I write that here, whatever I just now said, I write that. So this phenomenon happens, so this is because K is not normal, okay. So now let me write here what is the definition of normal. So K over K we write is normal, so is a normal extension if sigma and tau K to algebraic closure, I just write like that. If you are not very comfortable with algebraic closure and things like that, you just take complex numbers and you take small k to be a subfield of complex numbers. You can work in that specific context. Capital K, tau is another embedding, okay, or if these are field homomorphism or ring homomorphism, field homomorphisms, automatically they will be embedding field homomorphisms, then sigma k must equal tau k. This is the definition of normal field. So one nice thing is that if K is the splitting field of a polynomial f of x, then K is normal. And conversely, at least in characteristic 0, if you have a normal extension, characteristic 0 automatically it is separable and it is a splitting field of a irreducible polynomial. Let us assume that capital K is finite over small k, all right. So if this is a consequence of what is called primitive element theorem, I do not have time to go into primitive element theorem. I want to do lot more examples. If let us assume characteristic of K equals 0 and dimension of capital K over K is finite, then every normal extension, in fact extension is a splitting field of an irreducible polynomial. Okay. This is basically primitive element theorem. That's all. I don't want to say anything more. All right. So we made two assumptions. You have a normal separable extension. We are working with only finite dimensional field. We can work in slightly more general situation, but let us not do that for the purposes of this talk. So separability, you can almost forget about it. If you are working with characteristic 0, you will not go wrong. Okay. Normal extension is a basic thing that we would like to work with, and the reason why we want to work with normal extension is the following. Yes, I have still not formally defined the Galois group, maybe I should say. So, Galois group of capital K, I said that but did not write it. This is equal to set of all sigma k to k, sigma a field automorphism of k, capital K, such that sigma of x is equal to x, or maybe alpha is equal to alpha for all alpha in small k. That is the Galois group. Let us compute the Galois group of certain extensions. So, example. So, we had one, I wrote down 2 examples, and I am going to compute the Galois group of both the examples. What was the first example? K is equal to Q attach root 3. So, and small k is equal to rational numbers. In almost all my examples, small k will be rational numbers. If I forget to write that, just ignore, assume that. Okay, so now I will write down explicitly k to k. I could of course take identity, that is always there. Identity automorphism fixes every point of even capital K, so that is there. But other than identity, I take root 3 goes to minus root 3. This is an automorphism. Why so? Because root 3, well, so minus root 3 also is a root of that same polynomial x square minus 3 equal to 0. So, I can send this root 3 to minus root 3, and then just by direct verification, I have not really explained what I mean by that. Any element of this will be of the form a plus b root 3. I am sending this to a minus b root 3. Okay. This is an automorphism of the field. You can explicitly check that. Once you write down the automorphism, it is easy to check. So, what is the Galois group of? Yes. So, the Galois group contains at least 2 elements. Okay. Now, it is a theorem. Before I write this result and then write this, k over q in this case is actually isomorphic to z mod 2z. If I knew that there are only at most 2 elements, since I have exhibited 2 elements, it must be actually the group consisting of 2 elements, and that is of course z mod 2z. So, what is the theorem that I am using here? How do you know? I only know I wrote down 2 elements. How do I know it is exactly consisting of 2 elements? That is because of the following theorem. So, assume, yeah, we will always be in this case situation where capital K is finite over small k anyway. So, dimension of capital K over small k is equal to n. Then, so this is a theorem. Galois group of k over small k has order at most n. It can be strictly smaller than n, and the next example will show that. So, once you use this theorem, it has at most 2 elements, but we have exhibited 2 elements, therefore, it must be exactly 2 elements, and we are done. Is this clear? Now, let us do the other example of Galois group of q attach cubed root of 2 over q rational numbers is equal to actually only identity. So, it is a group, it is a trivial group. So, what is being asserted here? Let us look at it carefully and prove that. So, let us take this field k is equal to this field. So, I take a sigma field automorphism k to k, and I have this element, special element 2 power 1 by 3, that is the new thing which we have to attach to get k. Rational numbers are sent to rational numbers, nothing, you cannot do anything with the rational numbers, it has to be identity there, any field automorphism. Okay, now what can I send it to? What can it be? Okay, whatever it is, let us call that alpha. Alpha should satisfy the condition that 2 power 1 by 3 satisfies. What is the algebraic relation that 2 power 1 by 3 satisfies? 2 power 1 by 3, this side it satisfies the equation x cube minus 2 equals 0. So, that is 2 power 1 by 3, I take whole cube and then I subtract 2 out of it, I get 0. Now, once such a relation holds, I apply sigma to that, and that also I just compute the left hand side and see what happens. Sigma, so sigma of 2 power 1 by 3 whole power cube minus 2, but this is same thing, I can take the sigma inside because it is a field automorphism. So, this is same thing as sigma of 2 power 1 by 3, sigma of 2 whole power 1 by 3 minus 2 minus sigma of 2, but sigma 2 is equal to 2. Why is sigma 2 equal to 2? True, but why should any field automorphism fix all rationals? Well, sigma of 1, where can you send sigma of 1 to? Sigma is a field automorphism, identity has to go to identity. Yeah. So, 1 has to go to 1, if 1 goes to 1, then 1 plus 1 will have to go to 1 plus 1, and therefore 2 has to go to 2. You do not need to assume that every this sigma is an automorphism over Q, you can prove that. Any field automorphism, the moment it is characteristic 0, all the rationals have to be sent to, I mean it has to be identity on the rationals. Okay. So, this is equal to, but this I called alpha. So, sorry, I mixed up, alpha cube minus 2. On this side it has to be 0, this, therefore this must be 0. I can start off saying 0 equal to, because sigma 0 is 0. Okay. So, this means what? Alpha also satisfies the same equation, but how many roots of this are in here? Okay. There is only one real root, mind you, this was contained in R. We saw that the other two roots are purely, I mean are in the complex, the imaginary parts are not equal to 0. We already wrote down all the roots. Okay. So, there is only one real root, and that is 2 power 1 by 3. So, alpha has to be equal to 2 power 1 by 3. So, how do I conclude that? But this implies alpha has to be 2 power 1 by 3, because since alpha is actually a real number and satisfies this equation. Okay. So, that means that 2 power 1 by 3 also goes to 2 power 1 by 3, therefore it is identity automorphism. Once you know 2 power 1 by 3 goes to 2 power 1 by 3, 2 power 2 by 3 will have to go to 2 power 2 by 3. So, it sends a basis to a basis, done, finished. Okay. So, in this case, although the dimension of k over small k is 3, that same as the degree of the polynomial, that minimal polynomial that it satisfies, which is a cubic polynomial. So, dimension of capital K over K is 3, but the number of elements in the Galois group is only 1. Okay. This does not happen in the case of splitting fields, this does not happen in the case of normal extensions. Alright. So, now I suppose I have explained all the words that occurred in the main theorem. Yes, I needed to say a few words about this notation. So, let me come to that. Sorry, I had to erase this. So, okay. So, I said that f, yeah. So I had this following thing, let H be a subgroup of G, which is a Galois group of K over small k, and what is K power H? This notation occurred in the statement. So I explained this notation. This is set of all let us write alpha in capital K such that, so sigma of alpha is equal to alpha for all sigma in capital H, for all sigma in capital H. Is this clear? So, okay, notice already that if H dash is a subgroup of H and then you write K power H dash, I want to claim that every element of this is already contained in here. Claim is this contains K power H. This is one of the things I stated there in the theorem, but let us just quickly see this. This is equal to, so this is, see, you must think of this as condition on elements of H. Now, when you have fewer elements, fewer conditions are need to be checked. So, if okay, so this is a remark which is now clear, I suppose. If alpha, you take an element in here alpha in KH, that means sigma alpha equal to alpha for every sigma in H. In particular, for sigma coming from H prime also, this condition holds. So, every alpha in KH is already in KH prime. So, this condition holds. Now, I want to make this following statement. This is lemma or theorem, I don't know, lemma. If so, we will always assume characteristic 0 just to forget positive characteristic in this. If capital K, I can state it in a different way actually. I don't need to say anything, just there are, okay, let me say it this way first. If K is any finite extension, finite, so separable is clear now, finite extension of small k, then there is, then K is a subfield of a normal extension, finite normal. Extension. Well, it's a rather trivial thing to see. So, for E over K, it's simple to see because you write K as some small k. Okay, so I am going to write this as small k attach alpha. This is same thing as kx modulo some polynomial f of x, where f of x, where f is the minimal polynomial, minimal meaning monic irreducible polynomial satisfied by alpha, minimal polynomial of alpha. Okay, I take that. Then I look at the splitting field of F, then take E to be the splitting field of F. Take E to be the splitting field of K, splitting field of the polynomial Fx. Okay. So, I am going to illustrate this in the context of the extension Q attach cube root of 2. So, K example Q attach cube root of 2 power 1 by 3. This was not a normal extension, right, but we want to embed it in a normal extension. So, this is we saw, well, we have described this before, q x modulo x cube by x cube minus 2, and this is the minimal polynomial satisfied by 2 power 1 by 3. So, I take that, I look at, I want a splitting field for this polynomial. Splitting field means you just look at, you look at some algebraically closed field in which your small k is embedded, and there this polynomial will have all the roots, and you take all the roots, put them all in your field and look at the field generated by that, and that is a splitting field. So, in our situation, you all know complex numbers is algebraically closed, q is a sub of that. So, in complex number we even wrote down the factorization. I take all the thing. So, E is equal to 2 power 1 by 3 omega 2 power 1 by 3 omega square 2 power 1 by 3, but this is same thing as q attach omega and 2 power 1 by 3. Okay, is that clear? Now, what I am going to do is, I am going to illustrate the theorem that we wrote down for this particular extension. We are going to compute what is a Galois group, and we are going to see all the subgroups of this Galois group of this extension, and we will see how you can write down subfields of E, and at the same time the subgroups of this one, and you see the Galois correspondence. This is my aim for the next few minutes. Okay. First of all, what is the extension, degree of the extension? Degree means dimension of capital E over Q. Okay. So, you have two things in here, little complicated to work with. So, take one at a time. Okay. So, I am going to write E, this is okay, Q attach omega and 2 power 1 by 3. I just think of it as Q attach omega and Q. What is this degree of extension? Well, that will depend on the minimal polynomial satisfied by omega. Omega is cube root of unity, but itself not equal to 1. 1 is always cube root of unity. It is a primitive cube root of unity. Therefore, omega cube minus 1 is 0, but omega is not equal to 1. So, I divide it by omega minus 1, then it becomes omega square plus omega plus 1. Now, this is an irreducible polynomial, you cannot further factorize it. That means the degree of this extension, that is dimension of this over this, is 2. And what about dimension of this over this? Well, okay, again 2 power 1 by 3 satisfies the same minimal polynomial over here. Okay. So, this extension still remains 3. Okay. Or you can argue it the other way, you can first do it for here, from here to k, and k to here also you can do that. That also is okay. You can go from here to k is here, k is that field, and this extension we already know is degree 3 extension, and this omega, this is still a real field, and so omega being a complex number, it is not a sub, So, omega is outside of K. So, that also tells me it is 2. Either way, you see the degree of the extension is 6. I wrote down 2 other fields. There was also Q. So, I give myself a little more room here because I need that. I am going to erase it for a minute and then rewrite it. Q attach omega. Now, here K is already there. So, there is another field K1 and K2, and then I will have this picture. What is K1? So, this, let us call this K0. Ki is a field Q attach omega power, okay, K0 is, I is a wrong thing to write, say power R 2 power 1 by 3, R equal to 0, 1 or 2. K0 is same as K, alright. Is that clear? Now, notice, see from here to here this is already a normal field, here to here normal extension. That means from anything in between here to here also it is a normal extension. Okay. And in particular, what is the order of the Galois group from here to here? That is, for a normal extension, the order of the Galois group is equal to the degree of the extension. This was one of the things which I stated while computing for the quadratic extension, the Galois group. I said we have 2 elements. How do you know exactly 2 elements? Because it is normal extension. Same argument here. So, order of the Galois group when you think of this extension is 3. Any quadratic extension is always normal. And so, order of the Galois group when you go from here for this extension is 2, and this will tell us that the order of this, I mean Galois group of this over here, this is E. So, Galois group of E over Q, which you can also directly compute because you know the polynomial. Okay, anyway, let me write this. This has order 6. This way which I did just now. Now, how many groups are there of order 6 up to isomorphism? What are the groups that you know of order 6? 2. What are they up to isomorphism? S3 and S2 cross S3, Z2 cross Z3. That is same thing as Z6 cyclic group. Okay. Now, we know the Galois group is 6. Which one is it? Is it S3 or is it this one cyclic? Okay. Now, let us write down S3 here. Okay, you can experiment with S6, S3, and also you can experiment with Z6. I am going to first let us make a guess. See, we can compute it. We can write down all the elements, write down a presentation, write down all the relation, and we can finally decide yes, it is S3 and not Z6. But let us just imagine for a minute you made a guess without much thought. We make a guess that is it is Z6. Then you write here Z6. Z6 is a cyclic group. Okay. Therefore, the subgroups are easy to write. So, Z3 and then Z2, that is it. Okay, there is no relation. So, this is how the picture looks like. But look at what is main theorem of Galois theory. There is a one-to-one bijective correspondence between subgroups and subfields. How many subfields have you written down? You have written down K2 this is not equal to, okay, this is not the same, they are all distinct. K2 is not equal to K1, K0, but you have in between one more and then Q. So, this picture is not the same as this picture. Okay. You have exactly one subgroup, let us look at here, one subgroup of index 3, one subgroup of index 3, whereas here there are 3 subgroups of 3 subfields of degree 3. The degree of the subfield should match the index of the subgroup, okay, but that is not matching. So, this is a wrong guess. Let us write S6 now, S3, sorry, I keep saying S6, but S3. So, S3 we all know 1 sigma and tau. Let us think tau is for transposition, sigma is the cycle, 3 cycle. Srini, how much time do I have? Another 15 minutes? 15 minutes. I will definitely not exceed time limit. I will finish in less than 15 minutes. So, then sigma tau, sigma square tau. Yeah, I suppose 1, 2, 3, 4, 5, and then, well, this sigma cube is 1, tau square is 1, sigma tau square is 1, 1, 2, 3, yeah, sigma square, I left out sigma square. The cyclic group generated by that, I forgot about that. Now, see, you have these 3 elements, tau, sigma tau and sigma square tau. Okay. Now, okay, so this contains, let me write here this group generated by sigma, which is isomorphic to Z3, and that is trivial. Okay. The group generated by the 3 cycle, that is sigma, and it has order 3, so it is isomorphic to Z3. What about the group generated by tau, and that is isomorphic to Z2. Now, the group generated by sigma tau, it turns out also has to be a cyclic group. Okay. Sigma, you can just do this calculation, sigma tau, but that same thing as tau sigma tau or tau sigma tau inverse, both are the same. This is same as sigma inverse, which is equal to 1. So, you see the group generated by that is also isomorphic to Z2, and the last one sigma square tau, do the same type of calculation, this is isomorphic to Z2. So, I have these in between ones and they are all subs of this. Now, this picture and this picture looks the same, and notice S3 has a subgroup which is normal and of index 2. What is that? That is a copy of Z3 here. This is a normal subgroup. Okay. Here this was the Galois extension, and what is the Galois group of this? That is Z2. Same thing that that Z2 is quotient of S3 modulo this normal subgroup. I can take quotient only when it is a normal subgroup. So, I take the quotient, I get normal subgroup, and it has of course index 2, and therefore it is normal, everything matches. Is that clear? So, if there is any doubt in this example, you ask me before I move on to the next thing that I have in mind to talk about. So, you can sometimes explicitly work out, okay, I have a few more examples in mind. I do not know how much, okay, depending on time I may not be able to do all the examples I have in mind, but let me do the next one that I have in mind. So, this picture illustrates for you explicitly. All right, okay. So, now I have not done one thing, I have not told you what is this automorphism sigma tau. How do I realize that in here? Okay. Yeah. So, it is so tau you can take that to be conjugation, which corresponds to sending omega to omega square, okay. And sigma, what does it correspond to? It just sends, see there are, so tau, let me write here. So, for each, the picture will be complete only if I show ultimately that this is actually the Galois group. So, I should tell you what is tau doing and I should tell you what is sigma doing. Tau is easy, tau actually corresponds to conjugation, complex conjugation. Therefore, it fixes all the real things. So, tau of 2 power 1 by 3 is equal to 2 power 1 by 3 and tau of omega is omega bar, which is same as omega inverse, which is same as omega square. And now apply tau again. So, omega square then becomes omega power 4, but omega cube is 1, therefore, omega power 4 is omega. So, tau square has become identity because it sends the generators to themselves, and sigma, sorry, thanks. So, sigma, what it does is sigma permutes the roots of which equation? X cube minus 2 is equal to 1. So, you have 2 power 1 by 3, omega 2 power 1 by 3, omega square 2 power 1 by 3, sigma cyclically permutes that. That is it. Now, you see 2 power 1 by 3 had a special status previously, but here it does not. Now, it just sigma can permute that one. Yeah. I do not write that. Okay, sorry, I erased this. Now I am done with this example, so I erase everything. Okay, now let us look at this other example I had in mind, which is just take rational numbers and let us look at zeta nth root of unity. Okay, so primitive nth root of unity. So that means that zeta power n is equal to 1, but not for any smaller powers of n. Okay. Then I look at this field k is equal to q attach zeta. This is an example of what is called cyclotomic extension. So, in this case, let us try and understand. Okay, so so the polynomial that zeta satisfies is zeta power x power n minus 1. Okay, but it is not necessarily the minimal polynomial. Okay, it could probably satisfy smaller. Perhaps I should do an example because there is not much time. So let us take, what's a good example? Let us take p to be equal to 5. Let us take p to be equal to 5, n to be equal to 5. Then zeta power 5 equal to minus 1 is 0, but zeta itself is not 1. therefore I just divide by that one, zeta minus 1 I get zeta power 4 plus zeta cube plus zeta square plus zeta plus 1. In other words, zeta satisfies this polynomial x power 4 plus x cube plus x square plus x plus 1 equal to 0, and this polynomial is irreducible. And how do you see that? You see that by using for example Eisenstein criterion, and we can apply this and do this. So, this is an irreducible polynomial, and then okay, the moment zeta is there, or another way of checking this, let me say it, see the degree of this extension is the degree of the minimal polynomial that zeta will satisfy, and the minimal, see it is really, the general case is not too much more complicated, but let me just say it, what is a degree, because degree of q zeta over q is equal to the Euler phi function phi of n. Okay. Yeah. So, what is a Galois group? I do not have time, so I write quickly. Galois group of this q zeta over q, this is equal to, so now all right, so I here you can explicitly write out, this is what I want to do, I can explicitly write out the elements of the Galois group. How do I write elements of the Galois group? This is a problem. So, sigma suppose is from k to k a field automorphism. Of course, it fixes rational numbers, no need to say that. Now, sigma, what can it do to zeta? Zeta is an nth root of unity. Therefore, sigma zeta should also be an nth root of unity. What are all the nth root of unity? You can simply write down. The nth root of unity, well, are 1 zeta etc. zeta power n. Zeta power n minus 1, zeta power n is again 1. Alright. Now, sigma is a primitive nth root of unity, sorry, zeta is a primitive nth root of unity, and sigma is a automorphism. Okay. So, this has to go to zeta power r, where see if r divides n, then zeta power r will satisfy a smaller degree polynomial. Suppose r divides n, then write n is equal to r times s, then zeta power r whole power s minus 1, this would be 0. Okay, this is a simplification, rs is in. But then sigma zeta satisfies a smaller degree polynomial. I told you it is a primitive nth root of unity, it cannot satisfy any smaller degree polynomial. So, r cannot divide this, and that means that r has to be relatively prime to n. Alright. Okay. So, you take that, and what it means is that, so this with r relatively prime to n, and this implies that sigma has to be an automorphism of this group. This is a group now, okay, roots of unity form a group, sigma actually is a group automorphism of this, and you know what is a group automorphism? This of course is a cyclic group of order n. So, this means that this is a units in the ring Zn, and what is the cardinality of this? That is exactly equal to Euler phi function phi of n. See, if you look at Z mod n and then think of it as a ring, what are the units in that ring? That is precisely number of elements which are invertible in Z mod n. That is precisely number of elements which are relatively prime to n. That is exactly the Euler phi function. So, we know the degree of the extension is the same as now order of the Galois group. In particular, this is a normal extension. And in fact, you have proved more. You have proved that this is an abelian extension, in the sense that the Galois group is, you have actually computed the Galois group. Okay? Every such R gives you a Galois automorphism, and any Galois automorphism is of this kind. So that proves that the Galois group, so to conclude, the Galois group of this extension q zeta over q is actually isomorphic to Zn star, the units in that ring, which also has Euler-Phi function as this one. And here any subfield, well, now this is an abelian group, every subfield will automatically be a normal extension of Q, all those things you can say. And it is a non-trivial result that if you take any finite extension with Galois group abelian, then it arises as a subfield of this particular type of field for a suitable n. That is a more complicated statement to prove, and we will not do that. I will stop here. If you have any question, you can ask me. 2 minutes. Yes. Okay, so I can tell you applications. There are, I mean, this is just scratching the surface, not even. It has enormous applications in representation theory, in group theory, in number theory. But if you talk in terms of real life applications, well, I mean, if you work in Galois theory very well, you will get your salary in some math department. To that extent, I know the application. I am sorry, I don't know any other physical application. Thank you. So, once again, let me remind you to collect your participation certificate. Those who have not collected their TA, they can go to the office, which is in the main building, the first building that as you enter the institute, you ask the reception where the office is, she will direct you there. And now please join us for high tea. Before we conclude, we have one more pleasant duty to do, which I pass on.
Yeah, so I hope all of you enjoyed this program. Yes? It was good? Productive? Are you going to come back again? Okay. So to make this program a success, there are a lot of helping hands. And since we are concluding now, so first of all, I would like to extend our deep appreciation to our director, who has always encouraged us to conduct such programs without any, hitch. So we would like to thank, please give some clapping. And then, our registrar, Mr. Vishnu Prasad, and his team, they have worked day and night, for a few days to make this program success. I can't list I can't take the names of all the people, but it is just our office staff, which includes, people from administration, from media, from canteen, from, these small guys who are working day and night. So please extend, your appreciation to them. Okay. And I would also like to thank all our, speakers who have, done a wonderful job. So I think we will conclude this session, and that's all. Okay, so thank you very much for coming. Okay.
On behalf of the participants, we extend our wholehearted thanks to the organizers, Professor P. Sankaran and K. Srinivas. Let us join our hands to them. So, for 3 things. 1, well-orderly arrangement of lectures. 2, for bringing stalwarts in the subject concerned. And for 3, the good hospitality. We never forget this, sir. We thank you once again very much for the
Thank you.
all of you. Thank you. Thank you, sir.
Yeah, so please join us for coffee.